Hello and welcome to the webinar Carbonate Sulfur and Oxygen and Nitrogen Determination in Ferroalloys. Let me first give you first information about this webinar. All participants would get an email with a download link for the video after this webinar, so you are sure that you will get every information you need. Please feel free to ask questions during this webinar. Maybe the link for you is called question, or maybe it's called chat. Just try something. Maybe it depends on the software, how the function is called. You can also send questions to webinar@eltra.com, and then I can answer all your questions. And just let me shortly introduce myself. I'm Dr. Andre Klostermeier. I'm a chemist and I'm product manager at ELTRA since 2013. Webinar, we will talk especially about combustion and inert gas fusion analyzers, which are suitable for the analysis of ferroalloys. In general, there will be the following structure. We will first have an introduction about ELTRA, then we will talk about ferroalloys, about the chemical composition and what are there for samples in the world. Then we will shortly discuss CS analysis and OH analysis. So when you are not familiar with this technique, you just get a short introduction how this technique works in general. After this, we will have a chapter called number 5 here, Analytical Tips. This is especially interesting for people who already have an analyzer, or maybe they are getting some trouble during analysis and maybe they see some effects they don't understand. In this chapter, I will give you a short feedback about main topics, why maybe the result is different in comparison to the one you inspected. And then you have a short summary. In the following, I will switch off my camera, so then it's a little bit easier for me to understand. And then I have an external microphone and headset, so you will hear maybe a little bit different voice, but it's still me. So please enjoy the webinar and have a lot of fun. First, I would like to give you a short introduction of ELTRA. ELTRA is located in Germany in a small city, Hahn, which is near to Düsseldorf. Since 1981, we are focused on the analysis of the light elements called carbon, sulfur, oxygen, nitrogen, and hydrogen. And in addition, of course, we also have thermogravimetric analyzer. ELTRA started with carbonate sulfur analyzers in 1981. And since 2012, ELTRA is part of Werder Scientific. And after this time, we started in developing the Elementric series, which is called Elementric 1HP or Elementric CSI, which looks a little bit more modern than the gray units we maybe had before. And of course, we are still developing new analyzers, and please visit our homepage and our webinars to see what we will have in the future. Today we will focus on the carbon-sulfur and oxygen-nitrogen analysis of ferroalloys. In the following we will shortly discuss which properties ferroalloys have and which things are important for a correct elemental analysis. Ferroalloys is a really interesting group of chemical substances. On the one hand, you have the iron, and on the other hand, you have maybe a metal, maybe a semi-metal, or maybe a non-metal. This causes a real large group of substances which have maybe different technical features and maybe have also different chemical composition. On the one hand, these substances are easy to analyze with an elemental analyzers, but on the other hand, you always have to consider which kind of sample you have in front of you on the table to be analyzed, and then you have to consider some technical details. And this is the reason why we made this webinar. First, I would like to start with an example. Ferrovanadium, for example, can be available as ferrovanadium 40, ferrovanadium 50, and this does mean that the vanadium content could be between 35 and 85%. It's still called ferrovanadium, it's still called ferroalloy, but due to the different content of the alloyed element, maybe the chemical behavior during analysis is a little bit different. Beside the different content of the alloyed element,
The ferroalloy itself also can have different carbon, sulfur, or maybe oxygen and nitrogen content. For example, ferrovanadium 75 could have a content of carbon of approximately 0.1%, whereas ferrovanadium 40 could have a carbon content of approximately 1%. When you consider the typical usage of ferroalloys, which does mean they are used to alloy, for example, steel, then you always have to consider that carbon and sulfur and the content of other elements also influences the physical parameters of the steel which has to be produced. And this is the reason why a chemical analysis of these elements is really important. First, I would like to show you which influences carbon, sulfur, and oxygen and nitrogen could have on a steel sample. When you have a look at the carbon content, you will see influences on the melting point, of the hardness, and of course also on the strength and brittleness. For sulfur, it's like this, that the machinability and ductility is mainly influenced. Oxygen indeed is really harmful for steel because it can cause brittleness. Nitrogen is a typical alloying element and can influence the stability and hardness. And these details are very important when you sell and purchase ferroalloys, because when you add it to your steel and to your alloy, you also influences the content of carbon and sulfur in these samples, and this would also cause a change of physical parameters. A combustion or inert gas fusion analyzers are always specialists for, I would say, a special element. This means on the one hand you have carbon sulfur analyzers, and on the one hand you have oxygen, nitrogen, and hydrogen analyzers. So this is the reason why we start with carbon and sulfur analysis in ferroalloys. Besides carbon and sulfur analysis, it's also possible to analyze these elements with other techniques. You maybe have one of these in your lab. Optical emission spectroscopy, for example, is common as spark OAS or ICP OAS, and these optical spectrometers can be used for carbon and sulfur analysis, but the reliability depends strongly on the sample homogeneity, on the calibration of the analyzers, and also very small concentrations of about maybe 1 or 2 or maybe 10 ppm cannot be measured with this technique. It's also the same with X-ray, because you can measure very high concentrations of carbon and sulfur, but when they are present as a trace, it's not possible. In former times, combustion analysis meant that you use resistance furnace analyzer. So they just work like an oven that you put in your sample at temperatures at about 1000 or 1500 degree, and you combust your sample and measured carbon and sulfur. But this is not, I would say, recommended for in our days, because steel or ferroalloys sputter a lot, and under these conditions you will have a lot of destruction of, I would say, furnaces and tubes and all these things. So this is not a common technique anymore. And it's also problematic when you have a high titanium content, for example. In a resistance furnace analyzer, it's not possible to analyze ferrotitanium, for example. The common technique to analyze carbon and sulfur with combustion analyzers is the utilization of induction furnaces. For example, the Elemental Go and HP2. In principle, they are using the same induction furnace as in household, but the applied power is much higher. How it works in daily practice, I will show you in the following. Our carbon and sulfur analyzer with induction furnace is looking like this. It's called Elementric CSI, and it's a combustion analyzer with induction furnace and ER cells for detection of CO2 and SO2. It's compliant to all relevant international standards, for example, like ASTM E1019. This is relevant for steel analysis, and of course it's also compliant with ISO standards, which deal with CS analysis in ferroalloys, here ferronickel. It's very easy to use, and on the left side here on this picture you see the analyzer, and on the right side you see an optional autoloader. These units would be suitable for analysis of steel, and also of course for the analysis of any kind of ferroalloys. Every combustion analyzer with induction furnace is working the same way. And so the elementary CSI is also doing. You have a sample, you put on some energy, you have a chemical reaction and combustion, and during this combustion process you have the release of CO2 and SO2, which is detected in infrared cells. Carbon-sulfur analysis with induction furnace mean that you always destroy your sample because it is melted and it's oxidized, and this process releases the gases we need for detection. For those of you who have maybe a spectrometer in the lab and is measuring carbon and sulfur currently with a spectrometer, a so-called spark OES, I will show you the general differences. A spark OES needs a spectrometer sample, and then you always analyze the surface of the sample. This does mean you do not get into deeply in the sample, you're just measuring the surface. Usually this technique is very fine for homogeneous elements like which are present as homogeneous sample, for example, iron, molybdenum, manganium. They're easy to excite and they are easy to measure. Carbon and sulfur usually is present in low concentration, and this could cause trouble during measurement in a spectrometer. Combustion analyzers are very easy to use. You can apply not only a spectrometer sample, because you can also apply solid samples, you can apply drillings, you can apply powder, and this makes usage of combustion analyzers very easy. You combust the whole sample and you can make a wide range determination of carbon and sulfur. You do not have to take care of a lot of different calibration and reference materials. In practice, does this mean you take your sample, lock in the name in the software, then you take your sample, put it in a ceramic crucible, put in 2 spoons of an accelerator, then you place the crucible on the pedestal of the analyzer, press start in the software, and then everything is done automatically. The sample is combusted and the carbon and sulfur are released as CO2 and SO2 and measured in the air cells. The typical measuring time is about 40 to 60 seconds, and the whole analysis time, so the whole cycle time, is very short, and it's about 90 seconds up to 2 minutes. Here we have a typical example of an analysis of an ferroalloy, and here we use the ferromanganese. We use the BAM standard or BAM reference material for analysis and applied a typical sample weight of approximately 250 milligrams. As you can see here, we will get very repeatable results for this carbon sulfur analysis in a combustion analyzer. It's about approximately 7% for carbon, and it's about 37 ppm of sulfur in the sample. We used iron and tungsten as accelerator. One analysis needs approximately 1 minute and 30 seconds. And the black line shows here the combustion curve of carbon, and the yellow line, which is very, very small because the content of sulfur is very, very small, shows here the sulfur signal. And although the concentrations of sulfur are very low and the curve is not really looking nice, it's possible to get reliable results even at very low concentrations. For carbon and sulfur analysis in ferroalloys, we already have some already prepared application notes. This is a document which mainly deals with the carbon and sulfur analysis on one special samples. For example, here ferrochromium, or with high carbon content and low carbon content, and ferroniobium, ferromanganese, and for example, ferronitrated silicon. An application note contains all relevant information you need for the analysis. You need to have all the settings for the analyzer and of course all the applied accelerator. And at the end you will have some typical data. When you have a different ferroalloys and would like to analyze it in hand, you can of course send us some sample for testing. As seen before, carbon and sulfur analysis in ferroalloys could be very easy. You just lock in the sample in the software, put your sample in a crucible, add some accelerator, press start in the software, and then you get your results immediately after 60 seconds. And this is something which is sufficient to work for a starter. This does mean, in contrast to spectrometric methods, the carbon-sulfur analysis with combustion analyzer is pretty easy for a lot of alloys which are present in the ferroalloy industry. And this is something you always have to consider, that this is a reference technique which is very easy to use. When you would like to get information about your sample, then I would show you some more details on the next slide. ELTRA offers always a free of charge analysis. This does mean when you would like to know which carbon and sulfur content is present in your ferroalloy, just have a look at the website, find the local distributor, fill in a contact formula, and then you can send us a sample. Then it's easy for you to evaluate if carbon and sulfur analysis is suitable for you. You will see how good the precision is and how easy the analyzer is to use. When you already have an ELTRA analyzer and maybe see that you maybe are not sure if you get a correct result, of course it's also possible to send us some sample. Then we also can make a reference analysis and can support you with additional information. And in fact, that's it for carbon and sulfur analysis. And we will start in the next slides on oxygen and nitrogen analysis. As mentioned in the beginning, combustion analyzers are always specialists for a special element. So usually the measurement of carbon and sulfur is divided from the measurement of oxygen, nitrogen and hydrogen. Oxygen and hydrogen are even more difficult to analyze with spectrometry techniques, and usually this is very uncommon because repeatability and limit of detection is not sufficient for the customers. A state-of-the-art analysis for oxygen, nitrogen and hydrogen is inert gas fusion with detection via ER or TCD. This is, for example, possible with the Elementric ONHP2. The Elementric ONHP2 is an inert gas fusion analyzer which is compliant to all relevant international standards, for example ASTM E1019. It uses an electrode furnace for fusion of the sample, and the released gases are measured in an ER cell or in a TCD. It's not only suitable for the analysis of ferroalloys, but it can also be used for the analysis of steel, titanium, and ceramics. On first hand, the Elementric CSI, which is suitable for carbon and sulfur measurement, and the Elementric ONHP2, which is suitable for oxygen, nitrogen, and hydrogen analysis, look pretty the same. But the technique inside is something totally different. For carbon and sulfur analysis, you put your sample in a crucible, add some accelerator, and use oxygen as carrier gas. And the oxidation of the sample causes the release of CO2 and SO2, which is measured in infrared cells. In contrast to the CS analysis, oxygen, nitrogen, and hydrogen analysis is done with a different carrier gas. You cannot use oxygen because this is something which is in the sample and should not be present in the carrier gas. So the sample is always applied to a special zone which is called the sample chamber, and in this sample chamber the sample is freed of atmospheric gases like oxygen and nitrogen. Then the sample falls into a preheated crucible, and there nitrogen and hydrogen are released in elemental form, and the oxygen of the sample combines with the graphite of the crucible and releases carbon monoxide. This carbon monoxide is oxidized to CO2, and this is the same as in the CSI, which does mean CO2 is measured in an infrared cell. In daily practice, the analysis of oxygen, nitrogen, and hydrogen is pretty easy. You just log in your sample in the software, you have to weigh your sample, apply the sample to the sample port, put in your crucible on the lower electrode tip, and all steps then are done by the analyzer. You press just start in the software, then the furnace closes, preheat the crucible, and in the same time the sample is flushed with inert gas. After flushing and stabilizing, the sample falls into the hot crucible and the released gases are measured with an TCD and an ER cell. And at the end, you will also get a signal, a measuring curve, which is integrated and show the measured results. And this is a typical example for the analysis of ferrovanadium. We used a medium sample weight of approximately 150 milligrams and measured the oxygen and nitrogen concentration. Here we get an oxygen concentration of about 0.8% and a nitrogen concentration of 0.5%. for 7%. The deviation, even of multiple samples, is approximately 1% or 1.5%. And this would be the same procedure for every kind of sample. You just put it in the furnace, press start, and get repeatable measurements. Here we used nickel capsules to fill in the powder, and we also have a very fast analysis time of approximately 2 minutes and 30 seconds. For oxygen and nitrogen analysis, it's the same as carbon and sulfur analysis. When you would like to have a free of charge analysis, just go to on our website, have a look at the contact persons you have locally. Then you can download a contact formula and just send the samples to Hahn or to your local distributor, and then you get the free of charge analysis. And then it's a little bit easier to see how good and how reliable the Elementrax series would work for your kind of sample. The following slides are intended for those of you who maybe have some experience in analyzing ferroalloys. On the following slides, we will show you some tips and tricks which you have to consider when you process a lot of different ferroalloys, because different ferroalloys could mean that you have to consider the chemical matrix of the ferroalloy more in detail. A reliable carbon-sulfur or oxygen, nitrogen, and hydrogen analysis does always mean that you do not only have to take care about the analyzer and its settings, but this does also mean that you always have to consider the sample taking, sample preparation, and sample storage. In the following, I will just show you which effect an error in one step could have. Unfortunately, the sample taking process is not defined for ferroalloys in detail. I could recommend to have a look at the standard which is valid for steel samples. This is the ISO 7524 R7526. It's also the same as ASTM 1806. This does mean they use a special sampling unit for taking liquid iron, for example, to prepare the samples for a spectrometric measurement and also for gas analysis. Maybe this is also suitable for you to take samples from the ferroalloy. Another technique could just also be straightforward. It could mean that you use an evacuated quartz tube, which is holding in the mold of the ferroalloys, and then the liquid is sucked into the quartz tube, and then you also have a sample of ferroalloy, which could be used for CS and ONH analysis. Let's have a look at the sample preparation step. This could also mean that you have to consider a lot of details to make sure that you prepared your sample correctly. First step usually is that you mechanically remove contaminations on the surface. The second step could be that you prepare a suitable sample size. And the last step, direct before analysis, could mean that you use your prepared sample and clean it additionally with acetone. Regarding the mechanical removing, you have to consider that your abrasive paper or your file maybe contains an element you would like to analyze, which does mean, for example, when you have a silicon carbide paper and you clean your sample with silicon carbide paper, then you introduce additional carbide, and this is something which you don't want to analyze in the CSI. So this is the detail which is always important when you prepare your sample. The other thing is that you always have to consider to prepare a suitable sample amount, especially when you have titanium-based sample. You have to make sure that the sample size is suitable. This does mean, for example, for oxygen and nitrogen analysis, that you have to prepare a sample which is not more than 100 milligram. And when you would like to do hydrogen analysis in titanium-based samples, you maybe can use higher sample weights of approximately 250 milligrams. This is something which has to be defined before you start your sampling preparation process. Maybe you prepared your sample with a file and maybe prepared a suitable sample size with a sectioning machine, then it's also recommended to clean your sample maybe with acetone or pure ethanol. Then you have a clean surface and you can make sure that the surface is free of contamination and you get correct results. One thing which is especially important when you prepare powders, please consider that a high surfaced sample like a powder could be oxidized during storage. And this is pretty important when you have a look at the oxygen measurement. For example, when you have a prepared powder sample, please make sure that you store it under inert gas like argon, for example. Otherwise, the oxygen content in your sample will always get higher because you oxidize the surface. As mentioned before, the carbon-sulfur analysis in general is easy. That does mean that you prepare your sample, put in the accelerator, combust the sample, and get in results. But please have in mind when you have a very high alloyed ferroalloy, this does mean a content of 50, 60 or even 80% of maybe chromium, molybdenum or titanium, you have to take care of the prepared sample dimensions and sample weight. For example, high content of titanium, molybdenum or chromium could mean that you cannot use a standard weight of maybe 1000 milligram. You have to reduce it maybe down to 250 milligram. And also the applied accelerator could have an effect. For an analysis in ferroalloys, typically iron accelerator and tungsten accelerator is used as combination. But when you would like to analyze very low carbon content, for example 50 ppm, it is recommended to use a high purity iron accelerator. In contrast to a standard iron accelerator, the high purity iron accelerator does provide less blank value, and then you get more precise and more correct results. A fine accelerator, which is suitable also for every ferroalloy, is the tungsten tin mixture, which here is called at ELTRA cell. This accelerator can be used for the analysis of nearly every ferroalloy, but the disadvantage is that it produces a lot of dust. For carbon-only analysis, copper could be a very nice accelerator. It assures a smooth combustion and assures a reliable determination of carbon. The disadvantage of copper as accelerator is the release of copper oxide as fine particles. These fine particles of copper oxide could bound SO2, and this does mean that the measured sulfur result could not be reliable. So carbon as accelerator in general is only recommended, copper as accelerator is only recommended when you only like to measure carbon. One other thing which is maybe important is the calibration. On the one hand, you can use certified ferroalloys, but of course in the CSI, due to its flexibility, you can also use just steel samples for calibration. One other thing which is also recommended when you would like to analyze very low carbon concentrations, for example like 50 or even only 20 ppm, then you have to make sure that the crucibles you need for carbon and sulfur analysis is very, very clean, and we recommend a calcination at 1000 degrees Celsius for a minimum 1 hour. When you would like to perform oxygen, nitrogen and hydrogen analysis, you have to take care of a lot of details to assure that your analysis is correct. First step is the evaluation of the sample shape. In any case, powders have to be applied to a nickel capsule because you cannot apply a powder purely to the sample pot. You have to make sure that the whole powdered sample gets into the crucible, and this is only possible when you use a capsule. The other thing which is important is the applicable sample amount. On the one hand, when you, for example, have a powder, every capsule has a limited volume. This does mean in practice that, for example, your applicable sample amount is limited to approximately 350 milligram. One other thing which is important for a correct analysis is the application of a correct sample amount for different samples. When you have a very high concentration of oxygen and nitrogen, for example in the treated ferrosilicon, you have to make sure that your analyzer is capable to measure these high concentrations. This does mean, for example, that you have to apply a sample weight of 50 or maybe only 100 milligram to make sure that your channel is not saturated. So then you see saturation of your channel and cannot measure, for example, in the treated sample, then it's recommended to reduce the sample weight. The thing which is also important is the content of titanium. When you have a very high titanium content, for example, 50% and more, then you have to make sure that you do not use, I would say, a steel application. You have to make sure that you use the titanium application. And for titanium samples, the applicable sample amount is limited to 100 milligram for oxygen and nitrogen, and for 250 milligram for hydrogen analysis. In general, it is a good trick when you have a new sample and get irritating results. It's recommended to reduce the sample weight. Then you can test if you have a reliable measurement, because maybe the sample weight was too high for this application, and then you would get maybe just reliable results by reducing this sample weight. It's also possible the other way around. For example, when you until now have a very homogeneous sample and could apply 100 milligram of, for example, of ferrovanadium, then it could be maybe also suitable to increase the sample weight to see if you get more repeatable measurements with increasing of the sample weight. Correct analysis for oxygen, nitrogen, and hydrogen could be really tricky when you have a ferro-titanium sample. When the titanium content is 50% or higher, you have to use for a correct analysis a titanium application for ferrotitanium. And this does mean in practice for oxygen and nitrogen analysis, you have to utilize nickel baskets. When you have solid samples, just add the solid sample to a nickel basket. And when you have powdered sample, you have to fill in the powder into a nickel capsule, and the nickel capsule has to be placed in the nickel basket. When you use ferrotitanium and would like to make a hydrogen analysis, you don't need a basket. You just have to utilize 2 tin pellets which have to be placed in the lower crucible. Please keep in mind that the analysis power also has an effect on the correct measurement on ferroalloys. For ferrotitanium, for example, you have to use 5,000 up to 6,000 watt when you would like to measure oxygen and nitrogen. For hydrogen analysis, a lower applied power like 3,000 or 4,000 watt is suitable to get reliable results. And this is the thing you always have to evaluate for your special sample. This does mean, for example, that a ferrovanadium with a high vanadium content maybe needs more power in comparison to an analysis of a ferrovanadium with a lower vanadium content. You can start evaluation on your own, or maybe you can send us a sample that can help you to find the correct analysis setting. And this is I would say, tricky thing with ferroalloys and ONH analysis. You always have to consider the chemical matrix of the sample and maybe the sample shape of the sample, and also in addition the sample which you would like to analyze. Hydrogen analysis could mean something different as OH analysis. So please use the correct flux material, use the correct applied power, and use a suitable calibration material. And this could mean that especially when you have titanium samples, that you have to utilize not only steel samples for calibration, but also titanium samples for calibration. A general rule is written below. This does mean please try when you get irritating results, it's recommended to try something. This does mean play with the applied power, play if you need flux, and play to use the correct sample amount. There's no general rule. Just play with the sample weight, reduce it by the half, or maybe increase it to get a good and reliable results. Of course, you can always ask ELTRA to support you with knowledge. Keep in mind that it's also possible that you get irritating results, although you have a well-established method. When you have a well-established method which is evaluated and worked maybe for days and weeks, and you suddenly get irritating results, please check the status of the consumables, chemicals, and the analyzer. This does mean for CS analysis, for example, you check the chemicals if they are worn and maybe they absorb SO2 and CO2 because they are very wet and maybe the filling is a little bit compact. Check the cleanness of the furnace and check if the furnace is sealed. Especially when you are using tungsten tin as accelerator, it is possible that you can call that the leakage is caused by all the dust from the accelerator. When you checked for CS analysis all the chemicals and all the tightness of the furnace and you still get irritating results, then please have a look at the sample. Maybe it has a different color, maybe it has a different particle size, or maybe have a look if the homogeneity is not good enough, or maybe is not good as before. This is also a typical error for carbon sulfur and oxygen, nitrogen, and hydrogen analysis. The other bad thing is that you have to evaluate always the condition of consumables, which does mean consumables, baskets, accelerators, because they can get worn when they are stored wrongly. A good example, for example, is from another customer. The main guy who works with the CS analyzer was on holiday, and his partner, for example, has the tungsten placed in a special hood. But this hood, for example, was full of acid, and so the tungsten was contaminated and it was no longer possible to get reliable carbon and sulfur analysis. And this could be the same for every tool you use. Every tool you use for combustion and inert gas fusion can influence your results. And for oxygen and nitrogen analysis, the chemical status is even more important in comparison to CS analysis. Especially the filter before the TC cell can influence the nitrogen content in a dramatic way, because a 20 ppm standard can deliver 2000 ppm of nitrogen when you don't replace the chemicals before the TC cell. One other thing is also the cleanness of the upper and the lower furnace, and here also a leak check is recommended to test if you lose some gas. These things are very important when you get irritating results on a known application. Combustion analysis with the elementric CSI or inert gas fusion analysis with the elementric ONHP2 is always safe, fast and easy. The analysis can be performed by academic skilled persons or not academic skilled persons. This method is standard compliant to all relevant international standards, for example, ASTM E1019. Nevertheless, when you get, for example, stress with the correct analysis of ferroalloys, keep in mind that ferroalloy could mean something totally different. A ferroalloy with 10% of titanium is something very different in comparison to a ferroalloy with 90% of titanium. This could mean that you need different settings, and this could also mean different flux material and a completely different application. For a complete, correct analysis of ferroalloys, always consider not only the analysis steps, but also consider the sample taking and the sample preparation process. When you would like to have a free of charge analysis of your sample, please contact ELTRA on the website, your local partner, and then you can send us some samples and we can give you the feedback how good the CSI or ONHP2 works for your sample. For existing customers, it's also possible to send us some sample to give you some support. So now we are really at the end of this webinar, and I would like to bother you with things you don't need. I would like to take care of your questions, and I would like to wish you a very nice day and have a nice weekend. Bye.